So this is just the second part of section 3.4 on limits at infinity, horizontal asymptotes. So we're simply looking at more of these limits, a couple more examples here. So the first one has a square root in it, and what I really want you to see is that the square root of x to the sixth is the absolute value of x cubed. So I want you to notice that there is that absolute value there, because it does mean that the numerator and denominator are not exactly the same. Like, we can't say that because we have the square root of x to the sixth that that's the same exact thing as x cubed, but it's very, very close. We just have to kind of make like a small, like we have to kind of use logic here in just one small piece. But what it does allow us to do is see that we have, similar degrees there. And so we're still doing the same thing that we learned in the first video, which is to divide numerator and denominator by the term with the largest degree in the denominator, or just the variable part. So in this case, it's x cubed. So I'm going to take 4x to the sixth plus 1. I'm going to divide it by x cubed, and then in my denominator I'm going to take 3x squared plus 7, and I'm going to divide it by x cubed. Now, in doing this, what's going to happen is, I'll do another line here. I have 4x to the sixth plus 1 divided by, and then what I'm going to do is I'm going to change this into x to the square root of x to the sixth. And what that allows me to do is to bring it into the square root. So understand that, say, the square root of 9/4 is the same as the square root of 9 divided by the square root of 4. So we can take the square root of 9/4 and we can separate it, but we can also take something that is separate and put it underneath the same square root. And that's what's going to help us here. Now, in the denominator, it looks like I should have had a cubed here. Sorry about that. I'm going to have, I'll just simplify this one because it's ready. 3 plus 7 over x cubed. And now I'll come over down here and move it. So I'll have the limit as x goes to negative infinity. That will be key, the negative infinity. So now I have this square root, and so all of that's going to go underneath 4x to the sixth plus 1 divided by x to the sixth. So maybe I'll actually extend this a little bit here, like that. And then in my denominator, that one's already ready, I have 3 plus 7 over x cubed. And just due to spacing, I'll just bring it a little bit over here. So limit as x approaches negative infinity. So notice in my numerator, I'm going to have the square root of 4 plus 1 over x to the sixth. And in my denominator, I still have the same thing here, 4 plus 7 over x cubed. And really what I want you to see is there's something to think about here that we talked about in the last one, which is that anything with that division by a variable, especially anything that has a constant, is now that when we look at this limit, this piece is going to go to 0, and this piece is going to go to 0. Okay, and that's important to see. However, there's one thing that I haven't addressed, and that's the fact that because we're going to negative infinity, we do have to think about one choice that we made. And that choice is that we have this situation here. So what I want you to understand is, if we were to plug in some very, very large negative number here into this original, right, because that's what we're trying to find out, the numerator is always going to be positive, but the denominator is going to be based on whether x is heading towards infinity or x is heading towards negative infinity. So notice that if I put in a very large negative value for x cubed, that's going to be negative. I multiply it by 3, that's going to be negative. And of course, if it's some very large negative number, I add 7, well, that's still a very large negative number. And so my denominator as x goes to negative infinity is going to be negative, and a positive divided by a negative is a negative. So although I might want to say that this answer is the square root of 4 over 3, in reality, it's negative square root of 4 over 3, or negative 2/3. And when I started with this, I can see it. What happens is I end up, just having to pay attention to, am I going to infinity or negative infinity? Because if this was x goes to infinity, the answer would be 2/3. But again, what we're trying to understand is that with the rewriting, we're kind of negating the fact that we're dealing with that positive, negative value that's getting larger negatively, because dividing by the x cubed, sends things off to 0. So, it's coming down to this idea that when I have this can be positive or negative. However, once I change it to this can only be positive. And so I have to pay attention to that just when I go x to negative infinity. So I have a feeling there's going to be some questions in the discussion board about that, but that's okay. Now next is the limit as x goes to infinity here of something with a square root. So you probably will not be surprised to find out that one of our very common tricks with this is to take what we have and multiply it by a conjugate. But we do have to pay attention to the fact that if I'm going to multiply it by its conjugate, that's going to be a numerator and denominator. And this doesn't have a numerator and denominator right now. So I'm going to have to give it a denominator so that I can see where I'm putting this multiplication by 1. So what you can do with these problems is, if you want, you can write out what you have and then pause it and see if you can do the multiplication. That's what I would have done in class, is have you try that out and multiply it and see what happens. Because the reason that we have to do this is, if you were just put in infinity right now, you'd get 9 times, infinity squared plus 4, and then you'd be subtract the square root of that, subtract 3 times infinity. Like, you're basically seeing infinity minus infinity, and like, that's not a thing. Like, that's not 0, and it's not infinity. And so what we're trying to do is rewrite this so that we can actually find possibly a whole number limit. So we have limit as x approaches infinity, and then in our numerator we have 9x squared, looks like plus 4, because a times itself is, for a square root, is squaring it, and then minus 9x squared. Notice what just happened there, because that's going to be really helpful to us. And then in our denominator we just have the square root, 9x squared plus 4, and then the minus plus 3x now. So of course we're not surprised, we've got some stuff that simplifies, and now we have the limit as x goes to infinity, and we have 4 over the square root of 9x squared plus 4 plus 3x. Ooh, okay, looks kind of funny, but you get it. And then at this point, it's okay to basically say, you know what, we have a 4 in our numerator, that is just a constant. Our denominator has values of x in it. Our denominator is getting bigger and bigger and bigger. The point that I'm trying to make here is at this point, we can now say, hey, this whole denominator here, because notice the addition here, is going to infinity. And 4 divided by infinity, 4 divided by something that's getting bigger and bigger and bigger and bigger, is just 0. So that is a real number, and that is the limit. And you can go ahead, if you want, you can graph that function, the square root of 9x squared plus 4 minus 3x, see what it looks like in Desmos, and you should see as we go out to infinity that this function does approach 0. Okay. So now just a little bit about trig functions here. We have the limit as x approaches infinity of cosine, and of course I just put a graph here of cosine so you could be reminded of what cosine looks like. Cosine oscillates. We know that the range of cosine, the y values are between 1 and -1, and so we know that. So when we think about this limit, as x goes to infinity, this thing just keeps going up and down. Cosine just keeps oscillating up and down, up and down. And so we would not have a limit in a case like this. This would be does not exist. It doesn't go out to infinity because it goes up to 1 and back down to -1 and up to 1 and just does that infinitely long. So we would not have a limit for this. However, when we look at something like the limit as x goes to infinity of cosine x over x, there is some things that we can do. So you may remember that we have the fact that we can, look at cosine as between -1 and 1, as I just wrote. And then you may remember that we used a theorem called the squeeze theorem to solve some problems back earlier in the semester, and that's going to come back. So I want to make this look like what I have right here. So to do that, I'm going to multiply my 3 sides by 1 over x, because I'm going to do it to all 3 sides. So because this is true, if I multiply through by 1 over x, this is still true. And now, of course, the idea is if we look at, I think I have this space here, the limit as x goes to infinity of all 3 of these, and again, you can look back at your squeeze theorem if you need to, limit as x goes to infinity of the middle piece, and the limit as x goes to infinity of the right-hand piece. Well, from earlier on in the section, we have these properties, and they have told us that this limit here is 0, and they've told us that this limit here is 0. We learned that earlier. So I'm going to bring it up here, and that tells us that 0 is less than or equal to this limit as x goes to infinity of cosine x over x less than or equal to 0. And so it's squeezing that limit and telling us, well, the answer to this must be greater than or equal to 0 and at the same time less than or equal to 0. So it must be equal to 0. Thus, limit as x goes to infinity of cosine x over x equals 0 due to the squeeze theorem. Okay. So I'll put it over here as well. But that's a place where we might use a limit to infinity, but with the squeeze theorem. And then the last part of this section is just how this helps us graphically. So when we start graphing functions, well, we talk about graphing functions in the next section. The fact that limits to infinity help us is because they help us with our horizontal asymptotes. And that's really asymptotes. Okay. You can look that up if you need to. Okay. So what I did was I actually already sketched it just due to how I have to record these. But you can see it's a rational function. We knew this already. And we can find different pieces of it. If you want, you could pause and find intercepts. And that would be fine. Notice that the denominator here does factor. You can factor it if you want. So you may remember from, obviously, something we've already kind of talked about, but in pre-calculus, your vertical asymptotes here are going to be at x equals a -1/2 and an x equals 2. And you can see that, by looking at my graph here. But the vertical asymptotes are not what limits to infinity tell us. They're telling us what's happening as x gets very, very big. Are we approaching some number over here? Are we approaching some number over here? As far as intercepts go, if we let x equal 0, it looks like y is going to be a -1/2, and so we have that value. That's right here. Okay. We can see that if we let y equal 0, That's basically implies that when is the numerator equal to 0, and we can see that that never happens because it's always going to be positive. And the graph that I've already graphed for you shows that as well, that there's no x-intercepts. So now let's talk about horizontal asymptotes. So the idea here is, in terms of horizontal asymptotes, you'd be looking at the limit as x approaches infinity for the x squared plus 1 over 2x squared minus 3x minus 2. By doing this limit, this will tell you what the graph does as x goes out to infinity. So it's helping you to graph it so that you're not just doing a sketch of like, well, it goes that way. What is it actually approaching? And we can see from the first page of our notes that because the degrees are the same, we will in fact have an asymptote here. So the limit as x approaches infinity, I'd have x squared plus 1 over x squared. In the denominator, we'd have the 2x squared minus 3x minus 2 over x squared. And that is going to give us limit as x goes to infinity. We have 1 plus 1 over x squared. And here we have 2 minus 3 over x minus 2 over x squared. Yeah. And so you can see already, just from the fact that we've already done a problem very similar to this, that this is going to head to 0, this is heading to 0, and this is heading to 0. And so that's just going to leave us with a 1/2. And so what that tells us is that the horizontal asymptote is y equals 1/2. That is what the y value is that you're going to approach as you head out towards infinity. And you can see if you do the negative infinity, you get the same thing. So we have this y value here. I believe it actually looks like this. Remember, you can cross a horizontal asymptote, you just can't cross a vertical asymptote. So on one side it looks like it crosses, on the other side it doesn't. And but eventually they both approach that value. Now, if we were to do a number line, which is the same as like a sign chart, you're going to see that if we just put on the negative 1/2, so that is one of the asymptotes. We put on 2, that's the other asymptote, and I'll put on x being 0. I just want you to think about the fact that I'm not taking any kind of derivative here. I'm just using stuff that we've known from pre-calculus. But, you know, if we were to put in values, this would just tell us whether our y values are above or below the x-axis. And we'd end up seeing that we're above the x-axis here. So if we put in something like a really large negative number, we're going to have a positive value. And we're going to be below the x-axis, and then we're going to be above. So if we just put in values in between those back into our original here, it would just tell us, is the function above or below? So although the derivatives do tell us a lot about things like concavity and you know, local mins and local maxes, there's a lot that can be done without calculus at all. Calculus just helps us refine those graphs. So in the next section, we'll be just putting it all together and doing everything we can to try to graph functions the best way possible.